Hello, everyone. So it's a real honor to be here and also seeing lots of friends from wavelet times and then from compressed sensing times and from learning times. And OK, so only an engineer can give such an outrageous talk, with such a title. But, I'm standing on the shoulders of giants, which are mathematicians, and you will see. Also, I mean, my intent here is really like to give you some higher level perspective, because I've been working in those areas for many years. And so that, as you try to understand, maybe you take a more abstract perspective. And what was interesting in that case, it became much easier, as I became more abstract. And then maybe someone in the audience will say, OK, this is exercise number 3 in some, maybe French math book or Russian math book, but we'll see. OK. Anyway, it doesn't seem to be known by the community. OK, so you saw MRI, but so that's my background. So I'm in biomedical imaging. And so for quite some years, we've been concerned with the problem, inverse problems. And so variational formulation. So what you have here, you have some unknown quantity, for example, density of fluorophores, some physical device here, model like an integral operator that's taking measurements. And so you have noise here. And so what you measure here is essentially a blurred version and noisy version of your signal. So now giving the measurement S, you want to recover the unknown S. And so the way we, at least for many years, have formulated this kind of problem. So in the 20th century, we were formulating it like that with a 2 here. And then as we moved on to compressed sensing, it became clear that it's better to put a 1. But any one, the idea here is that if you minimize that, so what you have here is a consistency term. So you're like trying to recover S. So if you simulate the measurements, the MRI process on S, so you get simulated measurements that would fit the true measurements. And then you put here some regularization. And so this regularization will impose some constraint on the solution. And that's actually what my talk is about. But now what's the connection with learning? Actually, learning, you can also look as an inverse problem. But maybe like compared to what I just shown you, it's an infinite dimensional one. In which sense? Is that you are given these data points. So it's X. So are some vectors. Y can be some classes. Or some quantity of interest associated with this data. And so what you would like to find is a function f that goes from Rn to R such that f of x is more or less equal to y of m. And actually what makes learning hard is especially in high dimension when this high n is very large. OK, so actually the traditional approach, so I will be very historical here, is to introduce regularization. And so among the first people were Poggio Gerosi to introduce that in learning, introducing this regularization function. So you essentially take some operator, for example, derivative or gradient, and you will impose a condition on the L2 norm of your solution. And so then you can reframe the problem like that. So here you have a consistency. So essentially, you want this function that you're trying to guess here to actually be consistent with your data. And then you're just trying to minimize here this energy functional and getting the best possible fit. And actually, this leads to regularized least squares fit and actually the theory of reproducing kernel Hilbert spaces. And so that we have a complete understanding here about the solution of that problem. So machine learning, this is, OK, those people, Waba, Shulkopf, and actually this leads to kernel regressors. And actually when you're talking about ridge regression, so this is, the framework that's very classic. I would say this is pre-neural network learning, OK, so looking at this problem. So there's the very famous representative theorem of machine learning. So that's where it has been coined. So if you look at this problem, so minimizing of that. So let's put a little structure here. F is a function. So we assume the function is in some Hilbert space, and actually it's not any Hilbert space, it's actually the Hilbert space where here this would be the square norm associated with the Hilbert space. So somehow the regularization fits the metric of the Hilbert space. And now if your Hilbert space is a reproducing kernel Hilbert space, then there exists a unique reproducing kernel. And so what it is, it's a kernel, so it's a mapping here. The functions are in RD, on RD. So this is a kernel RD cross RD to R, and such that actually if you let this variable open and fix this one, you get an element of your Hilbert space. And the other remarkable property, and that's the reason why it's called reproducible kernel, is actually if you apply the kernel now is variable open, this one fixed to F. So actually what it will act a little like the Dirac, because it will exactly sample the function. Actually, well, okay, maybe I'm going too fast here. So then it can be shown, I mean, this is this representer theorem, that the solution of that type of problem actually is a linear combination of this kernel. And so here's the output variable of the function f. And what's important here is the data where it sits tells you where to put your kernels. And for example, those could be Gaussian kernels. Now, this supports all the classical theory of support vector machines, kernel methods, kernel PCAs, etc. I mean, there's a huge literature on kernel methods. Now, the formal, the structure of this problem is actually that this kernel here is actually the representer of the Dirac located at x0. And this star here refers to an operation that's called the Riesz conjugate. But that will be super important in my talk, okay? So is there a mother of all representer theorems? So that's, a question you can ask yourself. Okay, what could we change here? Okay, so I have y minus, it was point values. Here maybe we could be a little more general, put linear functionals. And let's say put here, some squared norm. Now the classical representer theorem in machine learning, actually here I'm using x prime, but classical machine learning, this x prime would be just h. So Hilbert space reproducing kernel. Hilbert space in classical machine learning, those guys are just point functionals here. And so there are many people associated with this. Maybe for those who don't know, actually, I think the precursor of those methods is really Carl de Boer, because in a paper in 66, actually, he showed really, he used this formalism of reproducing kernel to solve some spline problems, and so he had all the machinery there already. Okay, so first generalization, Schölkopf noted that actually instead of taking the square loss, you can put any convex loss. And I mean, the same theorem still holds. Actually, you can also add, some convex function that would act on the function. And actually, it's a two-liner proof, but has lots of implications. And so now the question is, can we be more general? Okay, let's we heard about Banach space, so let's put a Banach space. Okay, I already told you here linear functionals, so let's put any linear functionals. Here, let's put any proper strictly convex cos functional, and here some arbitrary increasing convex function. Okay, so that's more or less the question. Okay, if we can solve that, maybe can claim that could be a mother. Maybe Ron already has the answer. But, okay, so that was my introduction. Okay, now unifying representer theorem. So I talked about Banach spaces, and actually here are the tools that will help us to uncover this representer theorem. So general notion of Banach space. So here's a nice picture of Banach. So a Banach space is just a vector space equipped with a norm, but such that the converging, all the converging sequences or elements in that space actually converge to a limit that's also in the space. So it's a complete norm space. So that's very, very, very standard. Now, okay, you ask yourself, why this abstraction? Actually, this abstraction is fantastic because there's so many things that are Banach space. We heard a few in the previous talk. So, I mean, the toy example is Euclidean space, Rn, okay? But, for example, in machine learning, they use linear spaces of functions like Sobolev spaces. But you can also consider spaces of linear functionals. You can also consider linear spaces of vector-valued functions. And so that's actually, when you have an output that's also multivariate. And, this is the ultimate generalization. Actually, we heard in Justin's talk, is linear spaces of bounded linear operators from a Banach space to a Banach space. Where the Banach space themselves could also be stuff like that, et cetera, et cetera. So, well, okay, there's some restriction, but I mean, this is really general. Okay, now, if you have a Banach space, now what's important is the dual of a Banach space. And so, as you know, so for basic functional analysis, it's just the space of all the continuous linear functionals acting on that space. And actually, the dual space is equipped with this dual norm here. And so that's the textbook definition. So it's just like defined as this supremum. So that's very classical stuff. Now, I talk to the engineers, okay? Because what is the most important inequality in engineering Cauchy-Schwarz? Okay, now, if you have a Banach space, you have for free the so-called duality inequality, and it's the generalization of the super generalization of Cauchy-Schwarz. Okay, and this is true for any Banach space. Now, what are duals of Banach space? So that's the formal definition. But dual of LP spaces, we also heard that in some of the talks. So they are the so-called LQ or LP prime, with P prime being the conjugate. And actually, if you look at this duality inequality in the case of LP spaces, actually you get the Hilbert inequality, which is also super important. But so that's really where it comes from. So any Banach space has its inequality. Now, if you look at, for example, this paper of Karl de Boer in 1966, you see that actually the tool here is the use of the Riesz conjugate. And actually, if you look at this duality bound for Hilbert spaces, which I said is equivalent to the Cauchy-Schwarz, but actually you rather write it like that, okay? You write it, okay, so here you have just a duality pairing. So let's say the U would be in the Hilbert space, the V would be in the dual. And so here you have the duality mapping, so that gives you a number. And this number here is bounded here by the product of the norms. And so here's the norm of U in the Hilbert space, and here the dual. Now there's the Riesz conjugate. And so that's also sometimes called the Riesz representer, and hence the name representer theorem. So Riesz conjugate is the unique element in the conjugate in the dual space, such that actually if you do the inner product, the duality pairing between U and its Riesz conjugate, actually this is the same as doing the inner product with U and itself in the space, okay? And so that by definition it's the square norm. And actually, if you use this inequality mapping, actually in this case also it gives you actually the product of the norm of U in H and the norm of the Riesz conjugate in H prime. Now what's important here is actually when you apply the Riesz conjugate, the duality pairing, actually you're in the condition where you're sharp here. Okay? And now the other important property is actually that the Riesz conjugate has the same norm as the guy. Okay, so it's the unique guy that has the same norm and saturates the Cauchy-Schwarz inequality. Okay, and this defines the so-called Riesz transform. No, the Riesz map. You can also, you have, actually it's a unitary map. You can invert it. So go from U to there and vice versa. So you have non-preservation. So it's invertible. So, you know, if I use this star, so I use the star to represent the Riesz conjugate, but then if you do the Riesz conjugate once more, you know, in the other direction, you are back. And the other important thing is actually the Riesz conjugate is linear. and this is only because we are in Hilbert spaces. Okay? Huh?
Real linear.
Huh?
Only real linear.
Yes, yeah. Okay, I mean, there may be subtleties with complex, but okay, we don't need them here. Okay, generalization. Actually, there's a generalization, and I must say, when I was doing my work, I felt there's a name to that. I just didn't have the right name, and after a while, I found it in the literature. It's just called duality mapping. I'm so sure many of you know it. So definition, let us consider a dual pair of Banach space. So x prime, then the element f star, which is in the dual space, actually the pair f star and f form a conjugate pair if actually we just take inspiration from Riesz, okay, if the norm is preserved and if the duality bound, this super Cauchy-Schwarz inequality is sharp, okay? And this will define actually the Banach conjugate. And actually now for a given f, so any element in a Banach space, actually now what may change is not necessarily a unique guy, okay? There can be a whole collection of guys, and actually those guys define the duality mapping. So I will say G of F is just the collection. So now it's a set of all the guys, that are in the dual space, have the same norm, and saturate the duality inequality. Now, okay, so that actually was introduced by Berling, Livingstone in 1962. And here I'm really happy because I'm standing in this room. Actually, you'll see the connection because Berling actually is one of the most famous Swedish mathematician. He's the guy who broke the code, of the German. Actually, the Gemeinfernschreiber, so it was like a typewriter. He actually pencil and paper in two weeks alone. He broke the code, and so during the war, actually. This helped the Ally also. I mean, on top of the Enigma and Alan Turing story. Okay, so it's very relevant. So that's the Berling. So I think it's super. It's a coincidence that it's just in this room, but okay. Anyway, so he was doing functional analysis on top of breaking codes. Okay, so what are the properties of the duality mapping? And those are the giants on which the shoulders on which I'm standing. Okay, okay. So now, and this mostly in Berling's paper and some other. Actually, there are books on duality mapping. So F admits at least one conjugate. So there's always a guy that will saturate the inequality. The duality mapping is homogeneous. Actually, now in the case where the conjugate is not unique, actually at least it's a set that is convex and weak closed in X prime. The duality mapping is single valued if, this is important, the Banach space is strictly convex, and it's also necessary in case X is reflexive. But actually, I want to go beyond reflexive, okay? But when X is reflexive, so what does it mean being reflexive? You take the Banach space, you look at the dual, and now if you take the dual again, you're back. If this is true, you're reflexive. Okay, so now actually we're very interested in the case where there's a duality map, we go in the dual space and we do it again and we're back. In this case, it's bijective and actually it is bijective, well, in the reflexive case, it's bijective if and only if actually the Banach space are strictly convex. So the good news for us is all the Banach space we usually work with, not all, but many, are reflexive and strictly convex. So here's the definition. Okay, mother of all representative theorems. So I must put here this picture because I have to tell you the story. It's not. It also involved my wife. Okay, like no, but we have a tradition in the lab. So I had a super good mathematician. And actually, he was so generous. So sometimes for birthday, he would offer a theorem to people in my lab. Yeah, you know. And so I decided, okay, now it's Christmas. Okay, I was thinking about this thing, and oh yeah, I think I have it. And so I was all excited, but I had to wrap the presents, and I was trying, you know, to prove the theorem. And my wife was saying, "Hey, are you finished with wrapping the present?" I said, "Yeah." Well, anyway, okay. So I just managed to wrap the present and send the preliminary version of the theorem to some of my students. Okay. Anyway, so what are the assumptions here? So the assumption is that we have a dual pair of Banach spaces. Now we have some linear functionals that are linearly independent. And actually, there's only one assumption. It's quite technical. Is actually that the function should be weak star continuous on X prime. And so what does this mean? Actually, that's important in the formulation. Because you wonder why there's an X prime. It looks a little ugly. Okay? You would prefer to put X. But actually, this theorem only works for spaces that have a predual. Okay, so, and if you know the predual, if the guy is in the predual, you're guaranteed that it's a weak star continuous. Then this guy is just a proper strictly convex loss functional. This guy is an arbitrary convex function. Here comes the theorem. Okay, the mother or father, and maybe it's well known, but I hadn't seen it, okay? It was just there to grab. For any y, the solution set of the generic optimization problem this, so it's just any Banach space, is non-empty, convex, and weak star compact. You say, well, what's the big deal? Okay, it just means the solution exists. Okay, well, that's a good start. Any solution F0 of this set is the X' conjugate of a common guy that lives in the span of the measurement functionals with suitable weights A. Actually, this is interesting, like Ron was talking about this manifold. And actually, somehow, here's a linear manifold that's spanned by the measurement functional. And then this X' Y conjugate, what it will do, it will curve it. So it will create the nonlinearity that's on top. Now, the nice thing with this theorem, I didn't need any Freche derivatives, subgradients. It's completely soft, you know, like just applying nonlinearities, inequalities, and checking when they are sharp. And if X is reflexive and strictly convex, and this guy is strictly convex, then the solution is unique. And F0 is now the Banach conjugate of this one, and it's unique. You can write it like that. If X is a Hilbert space, then actually this star, you can move it inside the sum, and you get the representative theorem, okay, of Schulkopf. Okay, so that's the theorem. So it's on archive. I mean, it's 2 pages, or maybe 3. It's not too complicated. That's the reason why I think maybe it's known. Yeah, but okay. Okay, optimization in specific Banach space. But I've never seen someone really point that out explicitly, at least not in the literature of practitioners. So how can we get actually the kernel theorem for machine learning? In that case, we take a reproducing kernel Hilbert space on RD. The induced norm is this. We have the reproducing kernel, and I said it's the unique representative of Dirac. And we're exactly the case, where this conjugate is unique, and it's a bijection, and in fact, the map is even linear. And then we have this learning problem. So that's the one that was on my Schulkopf slide. So arbitrary convex functional here. It's important. That's really a L2 norm, well, a Hilbertian squared norm. Lambda is your adjustable regularization parameter. So how does that fit in this general theorem? So in that case, x is h prime, and x prime is h prime prime, that is h, which is our Hilbert space. Now the linear function is Dirac. This function is this, it's convex. Our loss is additive, so we can write it like that. And we know there's the Riesz map. So the Riesz map is a mapping from h prime to h. And then we just apply the theorem. It tells us this. Okay, so that the solution now, because we're in the case of the Hilbert space, is just the linear combination of mu m star. And now the key observation then is actually, I already said it, is actually the star here is actually the reproducing kernel. And the reproducing kernel, you can also look at the Schwarz kernel of the Riesz map. And so that's this mapping that takes you from the dual space into the space. And the kernel of that mapping is actually your producing kernel. And so when you apply to those Diracs centered on the data points, you get exactly the kernel. So the kernel could be, for example, a Gaussian. You get the Gaussian centered on the data. And so that implies that the solution is unique and had that form. Of course, when the guy here is not quadratic, you don't have a closed form solution. You need to run an optimization algorithm, but at least the whole problem is discretized optimally. And so you have this kind of solution. Okay, let's move on. Here I advertise for my whiteboard presentation. Actually, in my whiteboard presentation, I will do this one because it's quite elegant. It will just be a warm-up. And then I will show you how this applies to neural networks, okay, that I don't have the time to cover today. But actually, this theorem, this mother of theorems, is actually relevant, for example, for showing that ReLU networks are optimum in a certain sense. So for those who are interested, just come to the whiteboard. Okay, so I'm not sure if it's proper to do advertisement, but anyway. Okay, so for Tikhonov, actually, what's really remarkable for Tikhonov, or the other thing, is we start with an optimization problem that is in infinite dimension. So we are optimizing over every possible function. And actually, the theorem says, hey, the solution lives in a finite dimension space, and it gives you the finite dimension space. Okay, it gives you the finite dimension space. It's just the Riesz map of actually the analysis functionals of your measurements. And so then it's the optimal discretization. And in this case, actually, when it's quadratic, you can even solve it in closed form. And so that's the equation of ridge regression. It's equivalent to ridge regression. Okay. So LP norm. So now let's go to.
You're going too fast for me. Can you go back?
Oh yeah, I'm just pressed by the time.
Is any lambda, and are you saying that? I mean, the solution has to depend on lambda.
Yeah. No. Lambda is your factor, your tuning factor. Like engineers like to have a tuning factor. So it's to adjust more or less regularization. But I mean, in this case, why is it so nice? Because you start really like with functional analysis, and you end up with a finite dimensional problem that's linear algebra. And so that's elegant, I would say. I mean, it's classical, okay? I mean, people have known that for, at least 50 years, I think. But maybe not everyone knows it. Okay, LP norm regularization. So this brings us to compressed sensing. Okay, now the goal here is to recover, a signal like of size n, given some measurements, and measurements are linear measurements, so it's linear functions, and possibly corrupted by noise. Compressed sensing scenario, we're looking at the case where actually the number of measurements is less than m. So can we recover? We know yes, but we have to favor sparse solutions. So how can we do that? We can just look at this version of the problem here. So we have the system matrix that's given by those linear measurements here. And we are going now to set it up as a LP, regularized LP optimization problem. So here we have our cost that favors data consistency. And here this constraint on the P norm. Actually, now if we apply the theorem here, it's actually in this case, X is Rn, but equipped with the LQ norm, the dual of which is Rn equipped with the LP norm, here with the two guys being conjugates. Then you have the discrete Hölder inequality. So that's the equivalent of I guess the Cauchy-Schwarz. I mean, duality inequality. Now, this function here is convex for p greater than 1. And actually, those two norms also are strictly convex. So we're in the easy case that there is a unique solution. Actually, we're in such easy case that actually the duality mapping is completely known. It's given by this. And I can just apply the theorem. And actually, this actually gives me the manifold of possible solutions. Okay, so now it's just, okay, the A is, I still need to find with my algorithm, but A is a vector of dimension n. M, excuse me, M, which is much smaller than the size of the signal here. Now, actually, if it's interesting to look at this Banach conjugation. And here, actually, what I made an animation. Now, it's interesting because if you take P equal 2 equal Q, okay, everything is equal. So here on this graph here in red, you have a random vector. And in blue, I don't remember, no, actually in blue you don't see. And the other color, it's conjugate, but for two, they're equivalent. So now what I will be doing, I will just be normalizing the V by the LQ norm just to ensure this isometry. And actually, I'll play a movie, and I just keep the same guys, and I will just compute the conjugate as I vary P. So see what happens? At 2, they were equal. So now we are getting to the case P equal 1. And see, now what there is, there's just one guy here survives, and all the others are tiny. And so that's the L1 scenario. So it's just this conjugate mapping just, like pushes them almost all to 0, and there's one guy that survives. Actually, to summarize here, 2 is identity, but this one is super interesting, is the L infinite. Actually, the L infinite, so again, so this is my original random vector. It's always the same, just rescaled for unit norm. And actually, the conjugate, it can only take 1 minus 1. Okay, and it's like this. And here you have, as you go here, actually P goes to 1, so Q goes to infinite. And there actually you have a really sparse solution. So it's one guy who survives and all the others get crushed down. Okay, so that's actually very interesting to look at those conjugation transformation.
Infinity, is this like a 1-bit encoding or something? What is this P equal to infinity?
I mean, it's just, it always takes the maximum. Yeah.
So
I mean,
what's
so,
the encoder of the signal? Takes 1 if it's positive, -1 if it's negative.
yeah. I mean, in some problems of engineering, we do L-infinite optimization, but certainly not in the compressed sensing scenario, because, you know, if 2 is not good, I mean, this guy is really like a total disaster. But no, it depends on your problem. But okay, that was the easy stuff. Now we get to the real stuff, okay. Sparsity promoting regularization. I mean, for now, I was in the reflexive case where I have a unique solution. Now I move to the non-reflexive scenario. So here's not necessarily unique, but I know that the convex set, the set of solutions is convex, weak, compact. And then what I can apply is the Krein-Milman theorem that actually tells me that, I mean, this convex set will be the convex hull of its extreme points. So that's just represented, graphically like that. And then we have a theorem here, and actually this is a theorem that I borrow from my French colleagues that I could just apply here. It's a relatively recent result by Boyer, Chambol, de Castro, Duval, de Gourmet, Weiss, that if I apply in that setting, that tells me actually that all extreme points of my problem, so F0, the minimizers here, can be expressed as a sum, a linear combination of elements EK here. And what are the EK? Actually, they're extreme points of the unit ball in your regularization norm. And so those are like, again, arbitrary coefficients. So it gives you also some kind of parametrization of the solution, but in terms now, in terms of extreme points of the regularization ball. So let me make this more concrete. Okay, so I said if there's a convex set, then actually a point is extreme if it's not an interior point of any line segment completely lying inside the set. Okay, so it's really at the boundary, but I mean there's nothing beyond. Okay. Now, what are the extreme points? So that's something I borrowed from Wikipedia, but I added the extreme points because they don't put them. So now here you have the unit balls of different LP norms. And actually, so you have all the LP norms. So the LP norms actually are not so interesting in terms of extreme points because every point on the boundary is an extreme point. So actually, this theorem of the French guy tells us nothing because actually the solution has, you know, any point here is an extreme point. But now in those cases here, for example, that's the L1 unit ball. Actually, the extreme points here are the sparse guy, and the L infinite is actually the corners here. So it's the 1 minus 1. Okay, so as I showed before. So actually here L infinite plus minus 1, here the Kronecker, and this one I would say any guy is an extreme point. So actually the extreme points are not interesting for the reflexive scenario. They become only interesting for the non-reflexive scenario where actually there's much less work in the literature. So now geometry of L2 versus L1. So it's actually interesting to compare those situations. So let's say here is a compressed sensing problem. You're measuring Y against a measurement vector here so that you get this value here. You're trying to minimize this optimization problem. So you're putting a slab here. So that's the sigma square. And now what you're doing, you're inflating your balls. And actually when you inflate this guy, when it touches at this point. Actually, this is exactly consistent with the representative theorem of Hilbert space because it says, I mean, if you apply to that case, it says actually that the guy has to live in the span of the measurement vector. So it says actually it has to live on this line. Now on the L1 case, it touches on the corner. But now what they never show you is the next one, because in compressed sensing, they always say it's unique. Okay, of course, when the restricted isometry is satisfied, it's unique. But actually, here's a case where it's not unique. But note that the extreme points are sparse. Okay, not the guys in between, but the extreme points are sparse. So actually, this theorem gives you quite some insight. I end up with Schwarz. Okay, so sparse kernel expansions, and so this would be an alternative to the usual kernel methods, because what I don't like is that the kernel have to sit on the data. And now let's just consider, so the test function, S prime, the dual, some regularization operator that goes from S prime to S prime. Then we define this native Banach space. And so this Banach space here will involve the total variation norm, which is actually, it's a sort of extension of L1 norm, but this is the norm of measures. Okay, and so what do we need here? Actually, for this to be a Banach space, we need the operator to be invertible. And in that case, actually, the kernel of this inverse is actually exactly what's called the Schwarz kernel of an operator. Every operator acting on test functions has a unique kernel. Okay, so I have to go a little fast, I'm sorry, but come to my whiteboard. we can develop that more. Now, okay, isometry with space of Radon measures. Actually, we have the space of Radon measures, so that's actually the elements of S prime. It's not the usual way they are defined, but we can define it like that, such that this norm is actually the supremum of this. And so what's the supremum? Here we're just, it's sort of the dual of L infinite, so it's the L1 that comes as a dual. But here we can use actually phi as being a test function. Why can we? Because actually this space here happens to be the dual of C0, and actually C0 is I mean, S is densely C0, so that's the reason I can write it like that. Okay, then we have isometries because this operator L is invertible, so I can define a bijection between my space that goes with the operator L and this space of measures. And I have also the kernel here. And now I need the extreme points of the measures, but those are known. Actually, they are Dirac's, just lying at points, any points with plus or minus. So the extreme points. So now I actually, because I have a isometry, a bijection, I can just apply my operator to those Dirac's. And what do I get? I get my kernel. Okay, I get my kernel positioned on tau k. And so therefore, if I look at this optimization problem, so it's almost the same as Shirkov, etc. It's just not a 2 here and not a Hilbert space, so there's a M. So that's a non-reflexive Banach space. And theorem, all extreme points can be represented as a sum of kernels. Now the difference is the kernels, they're allowed to move around. And what I didn't say also, actually they're less. I didn't say before, less than M. I mean here, equal.
Could be less than M or always M?
I mean, it depends on your lambda. Because actually, the other remarkable feature is that actually this norm here is actually equal to the L1 norm of the coefficients. And so if you agree that L1 norm minimization puts guys to 0, so the guys will get put to 0. So usually they are less. So they are less than data points. You don't know where they are. Okay, so that's would be this alternative. So special case of invariant. So I think I have to go a little fast. Okay, I mean if it's convolution operators, you can do the same as in conventional machine learning, going in the Fourier domain, looking for your inverse. There's also a complete characterization that you can deduce from Schwarz. Okay, so I think here is just a comparison between, let's say, the classical framework. This is sort of kernels living on the data versus this one would be sparse kernels. So it's the kernels. I mean, it's a much more difficult optimization problem because you also have to find where to put them. Okay, conclusion. So here we have a unifying result that supports all known representative theorems. So of course, you know, it's inspired. Actually, what's interesting is almost the method of proof is almost the same as with Hilbert spaces. If you are in reflexive and strictly convex Banach space, I mean, it gives you a unique solution. Here again, I always find a paper by Debo, you know, who did that in '76 for splines, okay? But I mean, more restrictive. You have Banach reproducing kernel reproducing kernel Banach space. There's also some work of Micheli, Zhuangzhu, Zhang, 2009, but not too much here. And that's reflexive. Now, modern sparsity-based optimization, so there's all the theory of compressed sensing. So it's actually many recent work, very interesting, for example, by Gabriel, Perret, Fernandez Gradac, Emmanuel Candes, on the recovery of spikes. I mean, that would be the theorem applied just to the M space. L-splines are optimal solution for inverse problems with generalized total variation regularization. I don't know if you remember that one I presented in Singapore. Yeah, no, but just to say, like, if you use total generalized variation as a regularization function, you find that any inverse problem is always splines, but with non-uniform knots that are actually a solution of that. So that's a Siam paper. And optimality of deep ReLU networks, so that come to my poster. Remarkable level of generality opens up perspectives. So Banach's, actually what's interesting here now, it changes a little the problem, because if you do an optimization, actually it suggests you better construct the space that matches your problem, because then you get the duality mapping, you get the extreme points, and you don't need to compute Freche derivatives. You don't need to compute gradients. I mean, everything comes for free. Opportunities for future extension, vector-valued matrix completion problems, operators and tensors. So it's exactly what you had in Justin's talk. I mean, all this fits. It's just because Banach spaces are so general. And so here I have to thank many people. In particular, like Julien, who's the guy who like taught me those kind of math. He was my PhD student, but he's from Normal Sup, so. Anyway, and here are some papers. And I think those that, I mean, the one that goes with what I just presented is on arXiv. And actually, yeah, the sparse kernel expansion is also here. So thank you very much.